Okay, but the question is, how did they get that static pushover for the entire building? Because each building will be different. So what they did is that they gathered lots of institute and lots of research funding, and they started testing the most common structural components, like the beams, like the joints, like the columns, with different criterias, with different characteristics, different material, and different dimensions. The tests were done under push and pull, earthquake. Lots of data were gathered. For example, this is a hysteresis curve, so force versus deformation. And what they did is that they got the backbone curve, which was connecting some points of the hysteresis, which we will discuss this in more details, how to get a backbone curve later on. But they were getting from a hysteresis, which is a push and pull, let's say tension compression behavior, they got just the monotonic curve that we discussed before as well, just one representative in, for example, the tension side. And this is the curve. Now imagine that you have a curve for every single possible component characteristics of a reinforced concrete. After a while you can see trends, so they started giving values for each bit. What happened is, for each component they managed to give a curve, whether force versus displacement or moment versus rotation. They got monotonic curves which was representing the behavior of that component. By giving values for A and small b, you can always plot these curves. Now, having these curves ready for every single component of your building, which is usually limited to few types of component. Anyhow, not every single column of your building is different. Usually we make all of the columns similar, so the construction will be easier as well. Now, if I have the curve, the behavior curve for that single column, it can be applicable to all other columns that my structure has as well. So if then I can get the performance of that column under, let's say, force, displacement, or moment, rotation, I can expand this to a general structural behavior. They came up with some tables such as this. For example, this is for reinforced concrete beam. This is the guide of the curve, and these are the values, for example, A, B, C, which you can use those to plot the pushover or the monotonic behavior of that beam, either in terms of force, displacement, or moment, rotation. They also gave a criteria of, in terms of, let's say, displacement of rotation, that if you have reached to any of these limitations, now whether you're the primary component or you're the secondary component, you have reached the immediate occupancy, the life safety, or the collapse prevention. So exactly like the pushover curve that we saw, that at any point there was a border between IO, LS, and CP, you can do that for every single component as well, considering these values. Now, how do you know which section is yours? By these values and some guidelines, you can translate the, let's say, the reinforced concrete beam you have or the reinforced concrete column that you have and match them. Now, if this property of your column is less than 0.1 or more than 0.4, then you can allocate one of these A, B, C's, and by just having A, B, and C, you can plot your pushover. We're still talking about the first generation of PBEE and what were their approach. It's just an introduction to this. Having the components, the structural component, let's say this, and then knowing that, okay, I have 20 of this kind of column, 30 of that kind of beam, we can allocate all of those, and there is a way to represent the global structural system. as a structure as a whole. So having all the components, beams, columns, joints together. Exactly what we do with the normal static pushover. So the software does kind of similar approach as well. For every single component that the building has in a simple pushover using Seismic or OpenSys, for each component there is a defined behavior curve, like a hysteresis curve, but just monotonic, just one side of it. Then it combines all of those, and at the end, the output that you see is actually just one single pushover curve for the entire building. You are able to see this curve for every single component as well. But what we are usually interested in is the entire curve for the entire building. Now, looking at this, I can clearly see that at this point is fully operational. At this point is immediate occupancy, and people can get back to the building and have the normal life with a little bit of repair. At this point is life safety. It's better that you have left the building, and during the earthquake it is safe for you to get out of the building. The building will not collapse on your head. And then collapse prevention and collapse onset, which is the last set. This will be dangerous bits. Usually it's irreparable, and you have to demolish the building and rebuild it again. What Eurocode usually designs the building with that 475-year return period and that elastic response spectrum that later on you converted to design response spectrum is mainly to make sure that life safety is provided for your design building. So we are still in first generation FEMA 273. This was the approach that they went. So they said, okay, instead of guessing how the building will perform, I will give a performance to every single component, and I can show this to my client that at different base shears, which I can kind of convert to different let's say shakings of earthquake and occurrence, I can tell it that whether the building will be operational or not, or whether it will collapse or not. Coming back to a little bit what we have seen so far, this is like a more simpler pushover curve. Again, base shear displacement, as we saw. Over here we have different types of building, let's say a masonry building, a parking, and let's say a reinforced concrete building. You can see at different points, different components are getting to different levels of damage. But for example, at this point that some of my columns are having a little bit extensive damage, but because not the entire building is having that extensive damage, my building is still at moderate stage. Does not mean that whenever the first column reaches, let's say, extensive damage, my whole building has failed. Structure acts as a integrated building, all components working together. So it takes some time to reach from moderate to extensive. You see, at extensive, a lot of elements are reaching that extensive damage for every single component, and at collapse, majority of my components, specifically let's talk about columns, at the bottom bit have reached very heavy damage. That's why my building has collapsed. The slide, usually we reach only yield. You see, only few elements are reaching yield. So always we give percentages. We say, okay, if we have slight damage in the entire building, that means that, for example, 40% of the columns at the bottom of the building, which are the critical ones which hold the entire structure, have reached yield. Not just one element reaching, because even at this point, with a simple push or with a simple force exerted for any reason, one element might reach yield, but that does not mean that the entire building has reached slight. So always have this in your mind, that the component based damage is a little bit different and is a little bit forward than the entire structure's damage. The structural behavior and the structural damage is usually delayed a little bit after every single component has reached certain criteria. Now, this was the first generation, and for sure it had some limitations. Let's look at some of its limitations. Now, one of the limitations was qualitative performance levels. It was vague and unclearly defined. What does really an immediate occupancy mean? It can be a little bit problematic to explain someone that, okay, after the earthquake, he can really see that there is permanent deformation, but that permanent deformation for the engineer might be safe. But for the occupant might be, no thank you, I'm not getting back to my building. I want you to fix my building, and then it is immediate occupancy for me. On the other side, explaining life safety to a client is a little bit hard because their standards might be different. Life safety for an earthquake engineer can be the fact that you can safely get out of the building and the building can collapse after you. But for a client, the life safety might be, okay, I will not lose a penny and there is no need for any repair. So there were some conflicts on defining these performance levels, which the first generation failed in doing it very clearly. Then there was some basic measures of system performance. The relationship between force and deformation, the relationship between components to the global system performance. All of these were a little bit vague, and every single engineer could have done it themselves. The fact that we were talking that, okay, you have the hysteresis or the monotonic curve for every single component, how is the most efficient way of gathering all of these to represent the entire structural performance? It's a very hard procedure, and if you do or miss some of the components, then it will be problematic because the structures that we have are not very simple systems. They have a lot of components, and every single component will have its own characteristics. Now, should I consider every single component of a building to do a performance? That will take ages, and it's very label intensive, and it costs a lot. So it was a little bit complex on applying every one of those performances for those components and then gathering them together to have a global system performance. On the other side, on another note, none of the non-structural elements were considered in the first generation. Infills of masonry, walls, partition, facades, windows, none of those were considered. Only major structural components like joints, like beams and columns were considered. And then everything was deterministic. All of the stuff that I showed you so far were certain values. There wasn't any probability, there wasn't any chance of reaching to certain points. So there weren't any variability in the nonlinear structural response. It was saying, okay, your beam is this, so this will be your performance. But is that 100% true? That was the questions that the researchers after the first generation faced and started thinking about it. Another limitation that was the problem, so far we were talking about pushover analysis, static pushover analysis, that I have the structure and I'm just pushing it in one direction. Is this really a correct way? Remember, this pushover that we do is kind of replicating the first mode of the structure. The first mode, usually, if you remember, is a transitional mode, which either the building goes to its right completely, or it goes to its left completely, or forward or backward. Now, what about higher modes that one bit of the structure, let's say the first floor and the second floor, goes forward, while the third floor and the fourth floor goes backward? Something similar to this case. You see, these two floors are coming forward while this floor is going backward. What happens like this? Some of them come toward each other, some of them go to the other direction. So the higher modes, let's call them, if this is T1, which the structure goes only to the right, all of the floors are going to the right, and this is T2, T3, and T4, what about T4 and T3? What about the fact that we might have a much taller building? Then what? For sure, that building will not go only in one direction. Each floor will have its own behavior. So this was a limitation of this pushover analysis, which, because the first generation was based on the pushover analysis, could not consider it. On the other side, when we push the building, we're just pushing it in one direction. But earthquake, as we know, it's not like as simplified as that. It strikes your building from every single angle, even it moves your building up and down. So that's a limitation of the pushover static analysis, which we didn't consider it. On the other side, the pushover analysis cannot capture very localized, concentrated deformation, like local bucklings. All of these are kind of ignored in this analysis. And then we discussed it before that material, for example steel, have a cyclic behavior. Because the earthquake is cyclic, the earthquake will push and pull your building. During this push and pull, you will lose strength, you will lose stiffness, and the building will lose its ductility and it will fail. A simple pushover couldn't replicate this. And so far, we haven't get into the details of the ground motion characteristics. It was just simply the occurrence of the earthquake based on the response spectrums that we had in the code from before. There wasn't any PSHA, there wasn't any specific calculation of the hazard that we are dealing with. So all of these, with the points that we discussed in the previous slide, gathered together and really question the first generation of PBEE, because you don't want to go back and cause more problem. You want to be progressive and solve problems and come up with solutions. So having that in mind, the second generation of performance-based earthquake engineering methodology was introduced. The background that you see is the Bird's Nest Stadium in Beijing, which was built for 2008 Olympics in China. It was again built by Arab, and some concepts of performance-based earthquake engineering was used in it. So identifying those issues and realizing that yes, there is a problem, some guidelines which started in 2010-2011, specifically in California. You see San Francisco, Los Angeles, and specifically for tall buildings. Anyhow, as we discussed, Chicago, New York, Los Angeles, San Francisco, they're always in competition for the tallest towers, who can build it taller. Now, those West Coast cities have the issue of earthquakes, and they have to deal with it. Unfortunately, the first generation was very problematic for them. Imagine how many components they had, how many different components they had, and for every single one of them, they had to get the information out of those pushover curves for every single component. It was very problematic in representing the entire building with a single pushover curve as well. So they came up and they suggested some guidelines and some suggestions. Those guidelines and suggestions has improved since then. For example, this is the Tall Building Initiative for 2017, or this edition of 2020 for Los Angeles tall buildings. All of these came up with proper solutions and solved majority of the questions that people were asking for the first generation. The main differences are some general design requirements were introduced that, okay, we will define properly the performance objectives. So your client will fully understand that if this building is built, it is going to perform under this and this and this under different earthquake intensities. They defined what is the design procedure and process and how that can be documented. They clearly defined how capacity design should be implemented in the design, the capacity design that the code suggested. How can we get the advantages of that in our design and get the benefit of it? Then they defined the criteria of the safety, which it was mainly based on the maximum considered earthquake. We will discuss about these concepts in coming slides. And at the end they said, okay, now that you built your building, you have to do a peer review. Someone has to make sure that you have done the correct design and how to provide that documentations. On the other side, they paid so much attention to the nonlinear dynamic analysis. So instead of a nonlinear static pushover, they moved on to nonlinear, meaning they considered the nonlinearity of the material, but for dynamic analysis, not a static analysis. This time, the input, instead of simply a push in one direction, was an actual ground motion. Let's say the representative earthquake accelerations versus time of that area. Modeling assumptions have improved massively. They included the damping of the material because they were like doing the proper modeling, which we will see. And they defined some acceptable criteria. What is the story drift ratio that is acceptable for such a tall building? Can it reach to 30 centimeters, or is it that too much? As well as the force control component and the deformation control components. So some building components, let's say, cannot reach to a certain force limit or deformation limit. So all of these were properly documented, and they properly wrote a guideline that can be applicable to other buildings as well. Now the second generation came and quantified these performance targets. What exactly means fully operational? What exactly means immediate occupancy in terms of replacement cost, casualty rate, and downtime? Now, if you tell these to your stakeholder, your client, the owner of the building, they fully understand that, look, whenever we reach, for example, the collapse prevention, the replacement cost is 100% of your building's cost. You have to demolish it and rebuild it. The casualty rate is about 25%, let's say. So 25% of the occupants of the building can lose their life. The downtime, for example, can be 180 days, 180 weeks, depending on the structure. So they fully understand that what they are facing. Similarly, for example, for life safety, the replacement cost is 50% of the cost of building your building from scratch. The casualty rate was 1%, and the downtime, for example, was just 30 days or 30 weeks. For example, FEMA and NERP have done a very similar estimation for a building. Either your building is new built or an older building. Now for each of them, they have unretrofitted old building or a basic retrofitting of an old building. You can see some braces are added. Now a basic code design for a new building or an enhanced code design, you can see some BRB braces are added to the building instead of a normal braces, or a protective system like base isolator, as you can see at the bottom of the building. Now they have considered, let's say, two case scenarios: major earthquake, 10% chance is 50 years, this is the 475 year, or extreme earthquake, which is extremely rare and it's just 2% chance in 50 years. This is equivalent to about 2,500 year of return period in the lifetime, the 50-year lifetime of your building. And as you can see, when the major earthquake strikes the protective system, no damage. When the extreme cost, again, no damage. There is only some shaking that the light is moving. But this changes when we move to the unretrofitted building. When the major earthquake strikes, proper damage, extensive damage. But when the extreme earthquake strikes the unretrofitted building, proper collapse or demolish of the building. Accordingly, let's say if we just look at the major earthquake and we just compare let's say the best building to the worst building, you can see the best building, the casualty rate is literally nothing, no one dies, but the unretrofitted building, the worst building, you really need like a proper consideration of casualty. Chances of post-earthquake placards. These placards are like whether your building is still immediate occupancy or not. So they put a green sign or an orange sign or a red sign. Red sign means this should be demolished and is dangerous. Orange sign means a little bit more repair is needed, and then there is a chance that the occupants can go back after the repair. And the green sign is that, yeah, it's okay, get back to your building. So you can see the best case scenario, green, the worst case scenario, higher chance of getting red. Expected building downtime. So imagine you just show this to the owner of a supermarket or a owner of a departmental store. They fully understand that if their building is properly protected with a protected system like a base isolator and a major earthquake happens, it's just a matter of some days that the building can go back to its operation. Now, if that supermarket or mall is based on unretrofitted old style building, years or more can take to rebuild your building under the major earthquake. Remember, it's not collapsed yet. We are talking about the major earthquake, not the extreme earthquake. So we have extensive damage, so there is a chance that we can repair it and rebuild it. Now, initial cost of these guys are different as well. For sure, the unretrofitted building was cheaper initially to build, and we invested very little. The one with the protective system, with the base isolators, designing it is expensive, implementing it is expensive, buying the equipment is expensive. So much more expensive than the normal one. But the repair cost is the opposite. Very little for the protected building, a lot of money for the case which was unretrofitted. They also even consider carbon impacts of the repair as well. Anyhow, when you're repairing it, you need lots of material. The more material you have to use, the more carbon you release. So now imagine showing this diagram to your client. They fully understand that, oh, so if that earthquake happens, this will happen to my occupants in terms of casualty and my business in terms of investment and downtime. So this was the second generation of PBEE, which helped a lot in understanding what is the consequences of those performance criteria, which was initially defined in the first generation, but it wasn't very understandable. So the second generation gave a quantity to every single one of the important concepts that the client cares.